A vital component of clinical radiology workflows is the accurate identification of MRI sequence weighting. Incorrectly classifying sequences leads to wrong downstream processes and unreliable, flawed outcomes. In this work, we explore the feasibility of using MedSigLip to classify MR contrast directly from pixel data.
My name is Susanna, and my teammate Luis and I work to fine-tune MedSigLip 448 for automated MRI sequence classification at scale, with the zero-shot classifier as baseline. Both Luis and I are scientific solutions engineers at Flywheel, where we create and refine containerized curation and analysis tools, we call them gears, for use on the Flywheel medical imaging platform.
Currently, data curation on the Flywheel platform often includes our file classifier gear to programmatically assess DICOM header metadata and assign a classification. Our team has designed a default profile for a few common modalities, and users can input an optional classification profile to expand on or replace the rules used to classify the image. However, this form of classification depends on reliable, complete metadata. Images that lack important classification-related metadata may not be adequately classified by this method.
MedSigLip's ability to accurately classify MRI sequence weighting by pixel data may be the answer to multiple problems. Being able to efficiently classify regardless of metadata availability is a powerful tool to leverage.
We utilize publicly available DICOM images for all training and testing. Before we could begin testing MedSigLip, we needed to pre-process the DICOM pixel data into the square PNG that the model requires. We started by isolating a single center frame, experimented on extracting equidistant frames, and landed on extracting the center frame across 3 anatomical planes and reaching a consensus. For our training labels, we utilized our existing file classifier gear to deterministically derived labels from the DICOM header metadata.
With our freshly converted PNGs and our ground truth labels, we evaluated the zero-shot classifier for baseline accuracy. MedSigLip's native capability to classify according to descriptive text prompts, such as a T1 weighted MRI scan, was only 27% accurate.
In an effort to improve this accuracy into a more functional range, we trained a lightweight classifier and frozen MedSigLip image embeddings from each of the 3 anatomical planes per volume. With our fine-tuned model, accuracy increased to 94.3%, with a 99.2% likelihood of the correct classification being in the model's 2 highest probability classes. Because our functional trial is integrated with the Flywheel platform, our code does have some Flywheel-specific components. We utilized our hierarchy curator gear to run the training script. This gear is specifically built to iterate through Flywheel's organizational structure and run user-created Python script, which is just what we needed to collect our files, run pre-processing and classification, and write predictions back to the Flywheel metadata. However, the core classification approach is platform independent.
There are a few details we believe would be great future steps towards making this MedSigLip-powered classifier ready for more general use. The datasets procured do not have an even distribution of all sequence weights of interest, and do not represent all anatomical structures that researchers would want to classify. Expanding the training dataset to include more representation of currently underrepresented classifications in anatomical structures may better ensure that the classifier generalizes appropriately. Another consideration would be to use more advanced models or data augmentations that may help train contrast features without anatomical features.
Thanks for watching, and thank you, Flywheel.